All right, so let us summarize what we've done in these videos about the electrostatic potential. V, which is a scalar function. So first of all, we considered a single point-like charge space, small q, located at some point capital Q, a source charge. Okay, in this case, as it turns out, we can write down a Colombian type electrostatic potential, which is given by V at any observation point capital P in space equal as 1 over 4 pi epsilon naught, as in Coulomb's law. But now it's easier because it's a scalar. And so we simply have Q divided by, instead of the square of the distance, just the distance itself between the source and the observation point. In general, this has to be plus a constant c, but we typically set 0 condition at infinity, and so we obtain a Green function for normal conditions at infinity. All right. So we also understood that there is an important connection between the work due to the internal forces, that is, the force, the electric force due to this charge small q, and the electrostatic potential. So for example, if I intend to compute the work, for example, if I'm moving along this line here, from a point capital P1 to a point capital P2 in this direction, and this is my line gamma, and here I place a test particle with charge Q naught, which I intend to move along this line, okay? The work due to the internal forces, so the work due to the internal forces, W along gamma from 1 to 2, due to the internal forces, can be very simply expressed by knowing the state function, which is the electrostatic potential, as Q naught. And now here you need to be careful. The typical mistake, this is V at the initial point minus V at the end point, capital P2. Great. So we found the work of the internal forces. All right? That's good. Of course, the work of the external forces is just minus sign that. We then generalized this concept to charge distributions, and the first distribution we encounter, as always, is discrete distribution. In this case, we just use the superposition principle, which applies also for the electrostatic potential. And so we end up finding, in this case, that the electrostatic potential V at any observation point capital P is nothing but the sum over all the particles in the distribution from 1 to capital N of 1 over 4 pi epsilon naught times Qk, the kth charge, divided by R Qk P, the observation point between the kth charge and the distance between the kth charge and the observation point. And this, we need to remember also here, plus a constant ck, but again, we set this ck to 0 for normal conditions at infinity. So this is the case of a discrete charge distribution. The other case is that of a continuous charge distribution. So if you have a continuous charge distribution, we simply need to move from a sum to an integral. Okay, and so we obtain that the electrostatic potential V at a point, an observation point capital P, due to any infinitesimal charge dq, is given by 1 over 4 pi epsilon naught volume integral, where the charge is distributed in omega, of dq, which is rho at point capital Q dV, divided by RQ p. We need to integrate this time. So we go from a sum to an integral. All right. We then gave a bunch of examples where we used, perhaps in 1D or 2D, an expression similar to this to find E from E, which is really what you want to do. And why is that? V scalar is much easier than a vector. However, we also found one example where from E we obtain V, so vice versa, which is not the typical thing you do. This is the typical thing you really want to do. That's it.